So good morning all once again. And in today's lecture, let's move ahead by having a quick recap of what we discussed in the previous lecture. So we started off the previous lecture about the backpropagation algorithm, right? Understanding the algorithm and its important aspects here, right? Like how to compute the error. Uh, yeah, is the slide visible? Anybody please acknowledge? Is the slide visible?
Yes, sir.
Okay. Fine. So in the previous class, we discussed what is this backpropagation algorithm, what it learns, and what it employs. Right? It learns the weight of the multi-layer network. The background aspect of backpropagation algorithm, it works on multi-layer network, right? And it employs gradient descent to attempt to minimize the squared errors. Right? It minimizes the error, and as you can see, this is the formula for computing the error, right? And if you see only if you ignore this part, so this whole formula is for the gradient descent. When we computed the error for the gradient descent, we used the same formula, and same formula is used here for the backpropagation algorithm with this one element added, that is summation of all the instances of output layers, right? The reason is because simply we have the multiple layers here, so we have to consider those multiple layers, which was not the case in the previous example. We took an example of linear unit or single unit perceptron, right? Single perceptron. So this is a multi-layered network. So hence we have to consider the multiple units in the output, right? So for that we have this additional term, which is nothing but the summation of all the units, output units. Then we saw the backpropagation algorithm, wherein we saw the different attributes the backpropagation algorithm takes. That is the the training example, which is the pair of input vector as well as the target output vector. Then the learning rate, number of input values, n out, number of output values, and n hidden, that is number of hidden units, right? Then we started off with first creating the feed forward network. Hope you recall by now. You must have remember the diagram of what we when we saw the multi-layered network, right? Hope you can recall that diagram. So we had a feed forward network there. So we set up a feed forward network initially, and once we have that network, which consists of all the input hidden as well as the output units, we go ahead and initialize the weights, right? Weights associated with the input values. So how do we initialize that? We initialize using random numbers, which is within a range. So the range that we have taken here, for example, is minus 0.5 to plus 0.05, right? Minus 0.05 to plus 0.05. So that's a example, just an example of a range that we can give to randomly assign the weights for the input, right? And then our actual algorithm start, wherein we do two important tasks, that is propagate the input forward, because it's a feed forward network, and we propagate the error backwards, right? So whatever the input that we have, we propagate it forward, and whatever the errors that we get or errors that we compute using the error term formula, those errors are given as the input to the, they are propagated backwards, and those errors are given as the input to the backwards units, right, in the backward layer. So these are the two important tasks that we perform. How do we perform these two tasks? Number one, that is inputting the uh, values forward, that is propagating the input that we get forward. How we do that? That is simply whatever the input that we get, we provide that input to the next layer, right? So whatever the output that we get from one layer, we provide that as an input to the next layer, right? So that will help us to propagate the input forward, and whatever the errors that we get, that we are going to back propagate it, and hence the name of the formula, the algorithm, backpropagation, right? So how do we backpropagate? For that, we need to have error terms associated to two units, right? The error term associated to output unit and error term associated with hidden unit, right? Please, these remember these formulas is very important. We'll see the algorithm also that how it works, but this is just you can say simple pseudo algorithm that will help you to understand what is the flow of the complete backpropagation, right? So how do we propagate the error backward? For that, in order to propagate the error backward, we need to compute two error terms. That is the error term associated to output unit, right, and error term associated to hidden unit, right. So the formula remains the same, which we have already seen previously in the previous lectures, which is this delta k. Delta k is the term that is for the error associated with respect to the unit k, which is a part of the output layer, right? Output unit. So delta k is the actually product of three things, which is output that we get, the difference of the range that is 1 minus the output that we get, and the difference of the targeted output and the output that we are achieving, right? That the output that we have got. So that difference. Now, one change here in this second computational, wherein we are computing the error term associated to hidden unit, the other terms remains the same. That is OH, which is the output for the hidden unit. Then 1 minus OH. These two terms remains the same. But as you can see, there is one additional term here, that is uh, the summation of all the weights and the delta k value. Delta k is what we have just computed here, right? So which is the error term associated to output. So summation of all those instances is going to give us the error term associated to the hidden unit. Now, once we have these both the error terms, our next job is to update the weight, because as you can recall, what backpropagation algorithm does, it learns the weight. Right? It tries to understand, analyze the weight that we are associating it with the input units, right? So it analyzes those weight. If there is a change in the weight depending on the change in the error, we will update those weight values, and we will see what is the difference, what is the delta value, what is the modification that we have done, right? So how do we update that? First, we need to compute the weight. So we need to initialize the weight, of course, first, which is actually the random, as you can see here in this second statement, initializing all weights, all network weights to small random numbers. And once we have these values, whenever we iterate, for every iteration, those weight values are updated. How it is updated? Whatever the current value of that weight is again added up with the change in the weight, right? Wherein delta W Ji stands for, it is the change in the weight from unit I to unit J, right? WJI is, it is the change in the weight from unit I to unit J. So that is the change in the weight that we have. Now once we add this change, we know the updated weight value now. But how do we compute this delta WGI, right? That becomes a question. So that we have already learned, if you can recall, delta WGI, the formula for that is uh, eta into the delta J value, which is the error term again, and xji, where xji is nothing but the input from unit I to unit j, whatever the input that we have for that particular iteration, that value plus, multiplied by the value of the delta j and the learning rate, where learning rate is any positive constant value. It can be any smaller value. Right. So we will have an example of this also, the complete thing. But this is what we discussed, and these are the same points which we have already discussed. But one major difference is that in the multi-layer network, that error surface can have multiple local minima. Right. This I have already uh, told you a lot of times that it has multiple local minima. So it becomes little difficult for the algorithm to select the global minimum value. Right. So it is not all the time necessary that it can converge to the global minimum error, right? It can, sometimes it may not. It's not necessary that every time it it is going to converge to the global minimum error, right? Because we have multiple local minimum. every time converging to the global minimum error becomes a little difficult. So, but the beauty of this algorithm, it is still more efficient algorithm. It produces still better results uh, for examples that are associated with real life practical applications, right? So that's why backpropagation is one of the backbone algorithm of artificial neural network, complete AI. Right. So we already had a discussion with respect to the choice of criteria, choice of termination criteria, when to terminate, right? Because the algorithm shouldn't be, underfitting, and as well as at the same time it shouldn't be overfitting. So that is important aspect that we have to take. Right. So another important aspect that we discussed was the adding momentum. If you can recall, it is just the same formula of weight, what we have seen, added the momentum. Right now, what is the job of this momentum? It keeps the whatever the the model running. For example, let's say we have a ball which has a rough surface, and if we add momentum to that ball, if the ball is rolled continuously, you can see there will be some changes in the ball and it smoothens up. Right? The rough surface gets smoothened up. So similarly, here in the model also, the more momentum that we add, not necessarily excess but adequate, not excess but adequate, right? So if we have adequate momentum to the model, then that error effect is going to smoothen up, and then when we will be having the appropriate output that we tend to expect. Right? So that's what the whole intention of having this added momentum here. So what is this momentum? It can be a positive constant again, which can lie between 0 to 1. So zero point 0.1 to 0.99, or uh, 1 or 0. It can be anything from 0 to 1, any value between 0 and 1. Right. So that is about the adding momentum. Now, very important aspect that we have to consider here is learning in arbitrary or cyclic network, right? Because example that we have seen so far is it is the cyclic network, right? But how can we make this model learn in an arbitrary acyclic network? I hope you know the difference between cyclic and acyclic. We already have understood this in a lot of subjects. Even in operational research, we have this network or cyclic network, right? So the weight update rule in this equation is retained. Now, what happens in this network is that we are going to keep some values unchanged and some values we are going to change. What are the values that we are going to change? Let me show you the algorithm so that it becomes easier for you to understand. Yeah. So in this algorithm, the equation T4.3 and T4.4, this is our main area of focus. And we are going to do some changes here so that it fits, right? I'll repeat. We are going to do some changes in these error terms to make the algorithm fit for even acyclic networks, right? It can, if we make those changes, then we can even apply this model, this algorithm for arbitrary acyclic network as well, right? So the only thing that we have to do is we have to keep the equation. Let me show the equation once again. We are going to, yeah. So we are going to keep the this equation same, that is t 4.5. We are going to just keep that equation same, and what we are going to change is we are going to change the equation t point 4.4, right? But how? Let me show you the weight update rule, that is equation t 4.5, which is the delta w value, if you can recall. It is retained, and the only change is to produce procedure for computing delta value. Right? Delta values, that is in general delta r. So we are going to add one more term here, that is delta r, which is a substitution uh, formula, you can say, for the formula that we have seen earlier for delta k as well as delta h. Right? Let me show you the formula again. But before that, just remember that this delta r, which is the value for a unit r, right? value for a particular unit R. Unit R can be any value. It can be from the hidden layer, it can be from the input layer, right? So any value for that unit R in layer M. Now what is this M? M can be input layer, N can be hidden layer, and M can also be output layer. So M is the variable which is denoting our layer there. Right? So M can is actually the substitution for let me so M can be either I, right? That is stands for input layer, or it can be H, that is for the hidden layer, or it can be O, which is for the output layer. Right. So once we have this value for a unit R in layer M, it is computed from these delta values at the next deeper layer. Right. So these value of unit R and in the layer M, we are going to compute in the next iteration. That is in the next layer. For example, if we are going to compute the delta value for the input layer, so we are going to compute that delta value only when we complete that input layer and we move ahead in the hidden layer. Right? So when we are in hidden layer, only then we can be only then we are in position to compute the delta value for the input layer, which is nothing but m plus one layer. So if we are computing the delta value for input layer, the value that we are going to get uh, that is in the hidden layer. So if the input layer is m, then the hidden layer becomes m plus one. Right? So that is the only difference that we have, and the delta R value, the formula changes to this. Right? So the formula 4.3 and 4.4, that is T 4.3 and T 4.4, will no more be retained. They will be changed to this formula, which is almost the same as what we have already seen. OR is the output for the unit R, the difference of the output, that is 1 minus 0 r 1 minus OR, and the summation of all the layers, whatever that layer is. Now layer m plus 1, as I said, m plus 1 can be H. So this will be S belonging to H, right? So that will be the replacement. And then the weight formula remains the same. WSR, where S is the layer, right? And R is the unit, then product the delta value for that particular layer. Right? So what where this formula we are going to substitute is, we are going to substitute this formula in case of these values, that is delta K and delta H. So instead of T 4.3 and T 4.4, we are going to use the formula equation number T 4.19, right? So equation 4.19 is the replacement for this thing. So instead of delta K and delta H, we are going to only compute for delta R. Right? So this is delta R. You can say. So that is the only change that we have in case when we want to put this model for the arbitrary acyclic network. Right? Now, in case, just in case that there are no uniform arrangement units, right? They are not uniformly arranged because these things are only possible when we have uniformly arranged unit, like because we are dealing with the equation m plus one, that is nothing but the current layer as well as the next layer. That is when we have the uniform layers, right? And we have the uniform values. So what if we don't have those uniform values? Right? We don't have those uniform units arranged properly. So in that case, the rule for calculating the delta value, right? That is the again error value, the delta value for any internal unit, right? Any internal unit which is not an output unit. It can, when I say any internal unit, it can be number one input unit, or it can be hidden unit. But output unit cannot be the internal unit, right? So this formula is only suitable for input and hidden layer. So if this is just an example, this is just a case scenario where let's say don't have a uniformly arranged units, then we have to uh, change the value for the delta, change the formula of the delta value, considering only the internal unit, that is accepting the output unit, and the formula changes to this, that is delta r, which is again almost similar to what we have seen, that is delta r is equal to OR, right, first element, then 1 minus OR, just for the change in the difference. But the real actual difference is here in this term, which is summation of all the uh, S belonging to the downstream, right? Downstream is what it is, nothing but it is the set of units, right? Downstream is the set of units immediately downstream from unit R in the network. So immediately after R, unit R, whatever the units that we have, these are our downstream. So whatever is followed by R is nothing but downstream of R. So S is one such instance from the complete downstream of R, right? So summation of those weight and the error product is what we are going to combine here to compute delta R. That is the only difference when we talk about when we don't have the uniformly arranged units. So that is the that's it about the backpropagation algorithm. That is the major changes that we can expect in the backpropagation algorithm, and these settings, these small settings, what we have just seen, these settings will help us to uh, modify the backpropagation algorithm as per the problem definition, right? As per the area of application that you're looking forward to apply as an artificial neural network, right? So that's about the backpropagation algorithm. But let us go ahead and yeah, let's go ahead and see the algorithm how it works, right? So I hope you guys have already installed the whatever the environment that you are comfortable with. That let it be Anaconda if you're working on Jupyter Notebook, or else you can work on Google Colab also. There's absolutely no problem with that. You can decide to go for Google Colab also, because there are some restrictions. Please take care of those. For example, you need to have good internet connection when you're working on um, Google Colab. But if you're working locally without internet, I would suggest really Anaconda Jupyter Notebook is a good option for you. Right. So with that, let's say that we have this application algorithm. Right. Let me open the algorithm for you. So we'll keep algorithm here. Yeah. Right. And we are going to just see how the program works. So that will complete your lab experiment also. So the moment when you open the Anaconda Navigator, you get something like this, as you must be already aware, and you can click on Jupyter Notebook Launch, so that you get the Jupyter Notebook. And once you click on that, you'll get some window like this. Let me refresh it. Yeah. So some window like this, which is your by default local directory, right? Local host directory. So what I've done is I've created already the file, but if you don't have it, you can just go ahead and click on new Python 3, right? So when you go ahead and click on new Python 3, you get a fresh new notebook to start with, and then you can start coding here. Right? So since I have already created the program, just close this tab and I'll just open the tab that I have here, right? So this is the backpropagation algorithm that I have coded, but with some minor changes, right? So what are these changes? What are these things that we are going to see now, right? So let's go understand line by line with the algorithm what are the things that we are doing here. So I hope you remember the algorithm for now. What are the three basic steps that we are going to do? That is setting up the feed forward network, that is creating the feed forward network, initializing the weights, and then propagating the input forward and propagating the errors backward till we reach the termination condition, right? So we are going to do that. So let me go ahead and show you the code for that. Maybe if you guys already would have started with the backpropagation algorithm, and you must have already got the output for that. But just for your understanding, because you have not yet tried, if you have not yet tried, this is just for your understanding, but this might not be the actual backpropagation algorithm that is expected from the lab perspective. Why reason is why? Okay, let me show you the syllabus for the machine learning lab. Okay, so we are discussing the lab experiment number 4, that is to build an artificial neural network by implementing the backpropagation algorithm and test the same using appropriate data set. This is very important, right? Build an artificial neural network by implementing the backpropagation algorithm and test the same using appropriate data set. Now, now this appropriate data set, since they have mentioned this appropriate data set, they have not defined what type of data set. So I will leave up to you, depending on whatever choice that you want to take with respect to whatever data set, you are free to do it. You can select your own data set for that and write the program with respect to that data set, that specific data set. Right? Please note that there are a lot of data sets available, and whatever the data set that you select, there will be a lot of differences in that. There will be different attributes in different data sets. Some might have few attributes, some might have more attributes. So depending on those attributes, the level of the details that we have in that data set, depending on that, you have to write your back propagation algorithm. Right? So what I'm going to do is I'm just going to put a general layout of this back propagation algorithm. Nothing specific to a data set, but everything except the data, any particular data set. So I don't want to pinpoint exactly one data set, any particular data set, because if I give you one data set, I know that everybody is going to follow the same data set. It's better for me to not to give any data set. I will leave the freedom of choice for you to select any data set which is suitable for the application algorithm. Right. So what I'm going to do here is I'm going to show you the application algorithm here by giving my own values. Right? I'm not going to use any data set. I'm just going to put my own values, hard-coded values in the program, and I'm not going to import any external data set, right? Any any external data. I'm just going to put some values and check do I get the output that is expected of me, right? Let us go ahead and understand what are the prerequisites, what is the exact code that we are doing here, what do they mean, what do they understand, and how do we analyze it, how do we get it, how do we say that's right, wrong, do we get the appropriate accuracy, are we near, are we very far, are we doing good, right? So we are just going to implement this backpropagation algorithm to see how it works. Right. Before that, let us understand line by line what are these things. Right. First, as I said, importing the numpy as np is very important. This is your header, right? Importing the numpy. I'm going to hard code the value for x, which is my input. Again, hard code the value of y, which is my input again. And then I'm going to just put up a formula for computing the array longitude, right? That is the maximum of array longitude using the inbuilt function called Amax. Amax is the inbuilt function which gives me the maximum value of the array, right? That particular X array. So what we are going to do is we are going to define the few functions, that is sigmoid function we are going to define. We are going to define the derivative also of the sigmoid function. So I have the sigmoid function, just a simple one line code. What is the sigmoid function? This is actually the function that we are going to see here, right? This is that sigmoid, right? This is that sigmoid function that we are going to compute it. So sigmoid function as well as the derivative of that sigmoid function is we have already defined it. And once we have that, we are going to set up few variables. Variables like epoch. I hope you all are aware with the term called epoch. Epoch is the number of iterations that you want to run your program, number of times you want to train your algorithm or your model for that matter. So epochs is the iteration, right? If I want to tell something to a small kid, and how many times should I tell that small kid to make him understand or make her understand a particular thing? So that number of times is called epoch. Right? So setting the training iterations is epoch. So I'm going to put, since these values are very small values, so I will not hesitate much to give them a larger iteration for that. If I have really big values, I might have to think that should I give a bigger iterations because the numbers are very huge, and if I give a large number for the iteration, the total time execution from my program will be really very high. So in that case, I'll just make sure that when the values that I have is very small, so the execution time is very less. So that means I can spend some more time to iterate complete thing, right? So that's why I can give a higher value, like for example, 7,000. You can give any. There's no restriction with that. Higher the value, the better, learning. But also you have to take care that it doesn't overfit the model, right? So you have to be very careful while selecting the epoch value. That is your termination condition, the number of iterations. Right. Then we are going to set the eta value. Eta is nothing but this learning rate, which is a positive constant, as I said, which is our this value. Where is this? Yeah, eta value. Right. So here also in the algorithm, as you can see, it is one of the input, one of the parameter eta value, which is a particular constant value. Learning, it is the learning rate, which is a positive constant like 0.05. So instead of 0.05, I'm just going to give a very small number, 0.01, because I want more learning. Right. So setting the learning rate is also very important. That is, if you have very small data set, you can consider having a bigger learning rate, that is zero point 0.5, maybe zero point 0.6, zero point 0.7. But if you have a really big data set and you are very much you know very much aware of the fact that you have to more focus on the accuracy of the program. You need to have more better accuracy, very critical, very accurate data. Then in that case, you can get better learning rate, that is zero point 0.1, 0.1 like that. So let us go ahead and give the learning rate as zero point 0.1. Then we are going to define the other value, that is input layer neurons, 2. I've just given 2 value, you can give any value. And hidden layer in neurons, that is 3. And output neuron for timing, I have given just 1. Right? We can give 2 also, that becomes a binary classification, because we have 2 output neurons then. So if the number is 2 output neurons, there will be 2 classifications that will be happening, because we have 2 units in the output layer. So once we have that, next is, let me show you. Once we have this feed-forward network ready, we are going to put the weight, right? Don't forget that we have to initialize the weight for the random values with some random values. So what I'm going to do is I'm going to assign weight as well as bias also. Right? Bias we have already learned. I'm going to assign the weight for hidden layer, bias for hidden layer, and weight for output layer and bias for output layer randomly. So using the random dot uniform function, this is an inbuilt function, right? Once we have that, we have the termination condition, and then we are going to simply propagate the input forward and propagate the errors backward. So let us set up the loop to do this forward propagation. So this is the forward propagation that we are, whatever the input that we have when we process it, when we have the output, that output is given as the input to the next layer, right? So that is a loop that we are setting here, and also we are back propagating the error. So what is the error? Let's say EO is the error output that we have, which is our Y is the output minus the output that we have got, right? And we are going to change the we are going to call the sigmoid function here, as you can see from the formula here, right? So we are going to call the sigmoid function, the derivative of the sigmoid function, and we are going to upgrade the value for that. And then we are going to compute how much hidden layer with respect to the weights that we have contributed to the error, right? So once we have that, we are going to compute the formula that we have for the, which is nothing but the dot product, right? This one. And then ultimately we are going to print that what is the input that we have, what is the actual output that we got, and what was the predicted output, right? So once we execute it, you can simply run from here, or you can just you can directly press shift enter, right? For example, here you have to just click on the cell. This is one cell. Since I have executed it 4 times, it is showing the execution time, that is number 4. But let's say I am into this cell, I have to just press shift enter is the shortcut key, and complete code inside that cell will be executed, and at the same time you will get the output, right? So What is now this output? Let us go ahead and see what is this output. The output that we have here is first the input. This is just for our cross check. Then the actual output and what is the predicted output. Right. So let's say we have this input that for 0.666 value we have one value, for 0.033 0.33, sorry, we have zero point 0.5 and so on. And for 1, if the value input value is 1, then we have 0.666 and so on. So these are just the numbers. It can represent any example. It can be with respect to driving a car, it can be with respect to teaching a model to learn a game, it can be with respect to detecting a speech, it can be anything. These values are associated, these numbers mean something. But let's not go into that depth. What are these numbers coming from? But let's say we have this input, and the actual output that is expected is 92%, 86, and 89 respectively, right? But when we compute this, when we have this predicted output, the values that we got was, instead of 92, we have 0.90, which is 90%, or you can say 90.3%. Then we have 0.89, which is you can say around 89%, right? And then we have 0.90, which is around 90%. So 90, 89, and 90 is the predicted output that we have, which is instead of 92, 86, and 89. So as you can see, there is a slight error. There is not much difference in the error, but yes, we have an error here. Our model is not 100% accurate, but our model is fairly accurate. It is still above 89 percentage, right? So that's a good model you can say that we have. So you can consider this code for your lab also. That's no problem. But you have to import the data set. You cannot hard code these values. I've just hard coded because if I use any particular data set, I know that you all are going to follow the same data set. So it's better for me to not to suggest any type of data set. I will leave up to your choice. You can select your data type, your data set for, right? But you have to make sure that you replace this code with the data set that you are importing and accordingly modify your program to fit to the attributes that you are taking in that particular data set. So that is all about the backpropagation algorithm, what it does, what it operates, how it operates, right? And what are the areas of application, what is the drawback, and these things, right? So it's a very, very important algorithm, very core algorithm of one of the core aspect of machine learning, which is artificial neural network, right? So it becomes very important for any machine learning engineer or a data scientist or a data analyst or anybody who want to get into this data science with respect to this algorithms and all. This algorithm is very important because it is one of the core algorithms. Okay, so with this, we shall, we comes to the end of the lecture as well as the end of this module, as well as the experiment number 4 of our lab. Right, so you can, if you have any doubt, you can ask it now itself, or you can, if you have any doubt in between, you didn't understand anything, you can, once the lecture is made available on YouTube, you can simply revisit that lecture and try to understand the things there. Right, you can pause wherever you felt like the program in the problem that in the program that I've shown back, problem, and you can make a note of it. Right. So with this, we shall conclude. If you have any doubts, you can ask me doubt. The session is open for anybody. Any doubt? Okay, then. So if there are no doubts, then we should conclude the lecture. Thanks for joining. We can meet in the next lecture. Thank you.